So, good evening, everyone. Welcome to week 2 of Analog Electronic Circuits course live problem solving session. In this week's problems, we'll be discussing mostly about MOSFETs. So, what do we understand by MOSFETs? What are MOSFETs? What do we understand by MOSFETs? Maybe we can start from the point where we left last time. We said MOSFETs are, first of all, active devices, right? We said MOSFETs are active devices. Now, any one of you, can you let me know like how many terminals does a MOSFET have?
Four terminals.
Yeah, but when we use a MOSFET, why don't we use all four terminals? First of all, what are the four terminals?
Gate, source, drain, and substrate, ma'am.
Yes, gate, source, drain, and substrate, or we call it body. But whenever we talk about any characteristics in MOSFET, or when we generally talk about MOSFET, or even when you see the diagrams, symbolic representation of MOSFET, we only talk about gate, drain, and source. What about body terminal? Why don't we talk about it?
The body terminal is short circuited with source, ma'am. That's why it's not about to do.
So, is it always shorted with the source? What do you think?
Not always, not always. Not always.
Not always, right?
Mhm.
So, in general, we always say that body is shorted with source, but actually, that is not physically possible to design a circuit or a chip with all terminals of body shorted with the source of a MOSFET during fabrication. It's a very tedious task, and it takes a lot of routing to do to short your body with the source for each and every transistor. So when you look at from a fabrication point of view, it's not always possible to short all your body with source. So when body and source are shorted, then there is no problem. But when body and source are not shorted, then this leads to a new voltage between body and source. We call it VSB, and it basically leads to change in threshold voltage. So we can use it for our advantage as well. So for say if you want to change your threshold voltage of the transistor that you have fabricated, so you can do it externally by changing this VSB, right? So this is a body to source voltage. This is something that we need to keep in mind. And yeah, MOSFET, in a MOSFET, body and source are not shorted always. Okay, with
Can,
that,
can I ask a question?
yeah, please go ahead.
Yes. So how we can get benefits from the device when we increase the threshold voltage? How this device we can we use why we may increase the threshold voltage? How we can get benefits from this?
You can modulate the threshold voltage, either increase or reduce, and there are few transistors which need to have like high voltage transistors. If in general, also when we talk about a technology node, in every technology there are transistors which are of high VT, low VT. You might have heard of high voltage transistors, low voltage transistors. In general, when a foundry fabricates, there are always these type of transistors which are like high voltage, low voltage. They have the different usage, and different purposes to serve. So, for example, if it is a high voltage transistor, then the currents that you'll get will be low. So, depending on that, you'll use it in a different domain. Whereas when the threshold voltage, so for example, if the threshold voltage of a transistor is high, then the leakage will be low. But if the threshold voltage of the transistor is low, your current will be high, but leakage will also be high. So those there are trade-offs, and for when you want to have an optimized circuit, you need to consider all these trade-offs and design your circuits accordingly. So that is where even high voltage transistors are used for different purposes. Low voltage transistors are used for other purposes. We do have different circuits, different paths, and all these use different transistors. So yeah, that's where it is used. So it is very important to keep a note that body and source are not always shorted. But in our case, majority of the times we consider them as shorted. That is the reason we don't even find body terminals in symbols as well, like the basic MOSFET symbols that we use. So, what are the basic MOSFET symbols that we use? So, this is like very basic MOSFET symbol, right? So this is for NMOS. This is for PMOS. Now in this, can you let me know A and B, which is NMOS and which is PMOS?
A is PMOS, ma'am.
A
B is
is,
NMOS.
sorry, I could not get you. Could you repeat again? So you're saying A is PMOS and B is NMOS.
Yes, ma'am.
Okay. So all of you, do you agree with this?
The opposite.
Okay. So somebody says that this is PMOS and the other one is NMOS. Yeah. So first of all, how do you figure out which one is what, right? And secondly, not to get confused, always whenever you see an arrow, fix that in mind that the terminal where you see the arrow is source terminal. Always. Okay? And secondly, so this is NMOS, this is PMOS. So the arrow always shows you source terminal. In PMOS, and second, the arrow also shows you the current direction. Okay? In NMOS, source is at lower potential compared to drain. In PMOS, source is at higher potential compared to drain. Is this clear? So these are the things that we need to keep in mind. Okay, so first of all, the arrow always shows you the source terminal. The second, in NMOS, the source is at lower potential, and PMOS, source is at higher potential. So always whenever you see a circuit, you will always see NMOS placed like this, whereas you'll always see a PMOS placed like this. So this is source, drain, gate. This is drain, gate, and source. Okay, am I clear? This is very
Yes.
important to understand
Yes, ma'am.
because your equations change when it is P type or N type transistor. And also the flow of current, flow of charges, everything depends on what type of transistor it is and how it will behave. So it is very important to understand these annotations. Okay. Now, so when we have, considering that body is shorted, we have three terminals. Okay, so how many ports do we have? Let's say it is a NMOS or PMOS. So always a port consists of two terminals, right? So one has to be a reference and other at which we will provide the potential. So let's say in this configuration, I'll consider this and this. So maybe this is our input port and this will be our output port. So if you have two ports, then how many different types of characteristics that you can get out of them? For a two port device, you can get how many characteristics? So, and if
Characteristics.
6 characteristics, can you name them? Like, what are the 6 characteristics that you can get out of your
Ma'am, three.
three? Okay. So, what are the 3 characteristics?
Common source, common drain, and
No,
common gate.
no. See, common source, common drain, common gate are configurations.
Yes, ma'am.
So, characteristics are different. Characteristics means graphs that
Two,
you get, like
two
input,
characteristics.
output.
Ma'am,
How
two,
many?
two characteristics.
Two characteristics
Transfer
drain
characteristic.
transfer.
Characteristics. Okay, we are talking about characteristics, right? Somebody said two. Can you name them?
That Enrique Ramesh.
What are the names of those characteristics? Somebody said two, right?
Drain characteristics, transfer characteristics.
Transfer characteristics is one. Okay.
One more is drain characteristics.
Drain characteristics. Okay, so you mean output characteristics, right?
Yes.
What about input?
Input is VDS for drain characteristics. Input is VDS corresponding ID at constant VGS.
Yes, but
Regarding
I'm
transfer
asking
character,
transfer. Yeah,
then
transfer can. When we say output characteristics, it is between output voltage and output current. Transfer characteristics, when we say,
VG,
we mean output current, input voltage. But
yes, yes,
I'm
yes.
asking, what's your take on input characteristics?
Repeat one. What then?
What is your take on input characteristics? Is it present? Is it absent? Like, what is your take on it? Whether there will be any input characteristics?
VGS versus ID at constant VGS because VDS remains constant.
No, no. So, see, when we say transfer characteristics, it is VGS versus ID, right? When we say output characteristics, it is VDS versus ID.
At
There
Considering
is
constant
the
no
VGS.
other,
current flowing through gate, so
yeah,
ID is IC is 0. So there will be
IG
no
is
input
0.
characteristics.
No input character. So, see, there is a input characteristics which will be VGS versus IG. But considering that there is no IG or IG is 0 in your MOSFET, we neglect this characteristics. But there are always 3 characteristics corresponding to 2 ports. It's 2 to the power n minus 1 characteristics. So always, because see, in case of BJT, you have 3 characteristics, right? Input, output, transfer. It's just here also there is input characteristics. But since IG is 0, we don't consider that characteristics because there is no information that you can get out of that characteristics. That's why the characteristic is neglected. But there is always an input characteristics present. So whenever there is a 2 port device, you'll get 3 characteristics out of them. Is this clear to everyone? So please keep this in mind. You will always have 3 characteristics in case of MOSFET 2, but it's just that input characteristics doesn't give you any information. So that's why it is neglected. But there is always a characteristics for input as well. Okay. Yeah, next we were talking about, somebody said common drain, common source, common gate, right? What are those? Those are configurations. We call them configurations. Yes, somebody raised your hand. You no need to raise your hands. You can simply unmute yourself and ask whatever
And why
if you
is
have.
it called transfer characteristic VGS versus ID?
Yeah. So transfer, because we are trying to connect input and output characteristics here, or input parameter and output parameter over here. If you look at your transfer characteristics very carefully, you can see that VGS is an input parameter, whereas ID is an output parameter. And you're trying to map these two. So one quantity is from your input side and one quantity is from your output side, and you are trying to map these two together. So that's why it is known as transfer characteristics. Whereas when we call, let's say, output characteristics, so there you see the voltage is also from your output terminal and current is also from your output terminal. But in transfer, one parameter is considered from input and other is considered from output.
Okay,
So
ma'am.
that's why
Thank
it is transfer.
Yeah. Is this ma'am for any two-port network, for any generic two-port network?
Sorry.
Is those are the main characteristics for any generic
Yes,
two-port network?
generic two-port network. So one will be the transfer, which basically gives you the relation between input and output. One will be an output-based characteristics, and other will be an input-based characteristics. So this is basic generic characteristics that you can get for any two-port system.
But there is no characteristics between output to input.
No, so transfer is something like input and output relation, right? So one parameter you take from output, other parameter you take from input. And mostly, since your input is something that you have in your control, so you always keep it as a independent, like you always keep input at your independent axis, whereas you see your output with respect to input, right? You
Mm-hmm.
never want to see your what should I say? Your input governs your output, but your output doesn't govern your input, right? So that's
Mm.
why transfer characteristics always, it is like the independent axis is always your input and dependent axis is your output. So that's how it
Mm-hmm.
is always. But it is actually, so it tells you the relation between your input and output port. So
Mm-hmm.
these
Mm-hmm.
three are basic generic characteristics you will get for any two-port device. Okay, hope this is clear. Yeah, now moving on to the configurations. So we have three configurations: CS, CD, and CG configuration. CS is common source. So here, what type of configuration is this? The one that you're seeing in this particular diagram?
CS, CS.
CS, because here source is common between the two terminals, right? Now, if I make somehow I can make my drain as common, then it will be common drain, which is CD. Yeah. And if I can get my keep my gate as a common terminal, then it will be CG. So when we say common, that means we will consider it as the reference, and we use the other terminal for extraction of input, like extraction of output or providing input. So this that is the basic idea. I could not get you, Kavya. Is no characteristics? Could you unmute yourself and ask? I could not get your question. Hello, Kavya. Are you there? No character of relation between. What do you mean by no characteristics? Okay, Kavya, maybe whenever you feel free, you can uh, unmute yourself and ask. Okay, so with this basic information, and yeah, depending on different configurations, the MOSFETs provide certain characteristics that we'll come across uh, in this journey of exploring MOSFETs and MOSFET based amplifiers. So when we say, so these are configurations which are CS, CD, or CG. We also call them single stage amplifiers. We also call them single stage amplifiers, and all these have their different functionalities and different behaviors. So we'll go through these one by one as we come across them through the questions that we'll solve. Okay. Now
I think
moving on.
Mamshi is asking, someone is
So
asking in the chat box, is telling, is there no characteristics between VGS and VDS?
so yeah, that is, I could not understand what does no characteristics mean. Uh,
Is characteristics, I think, means a relationship. So is
no
there a
characteristics
relationship between
developed by
VGS and VDS?
VGS, VDS. See, VGS and VDS are two independent quantities. What is dependent is always VGS and ID. So current is dependent on VG and VD, VGS and VDS. There is no relation between VGS and VDS. These two are completely independent identities, and so these are actually, if you consider, you can consider it as inputs. So you provide VGS, you also provide VDS, but the current is that you get as an output. So yeah, there is no characteristics between VGS and VDS because these two are independent quantities. And when we say a characteristics, it is between one dependent and one independent quantity, right? So VGS and VDS are both independent quantities. So that's why there is no characteristics between them. If that is what the question is all about.
Yes, yes, yes. Thank
And
you.
otherwise, maybe Kavya, if you can elaborate on your question, I can spread more insight into it. So, yeah, with this information, maybe let's quickly move on to our problems one by one. And just in case if you have any other questions, just don't write in the chat box because sometimes it is not very clear from the chat box. You can simply unmute and ask. Nobody is here to judge you, everybody is here to learn. So please feel free to ask. Okay. So
Excuse
come.
me,
Yes.
ma'am. As you are saying that VGS and VDS are independent parameter,
Yes,
that
yes.
means gain is independent of VGS.
Sorry, sorry.
Uh, that means gain is independent of VGS input voltage because gain
Gain.
is VDS upon VGS, right? Output upon input voltage.
Gain.
Yeah.
Oh, okay, okay. In that sense, you're coming. See, in how to explain this? So, what I mean by independent quantity is that VG, VGS, and VDS are not related to each other. So that means if I am providing some voltage to VGS, it will not impact my VDS. That's what I'm trying to say. So it is like if I'm giving 5 volts to VGS, then it won't directly impact my VDS to whether it increases or reduces my VDS or VGS. Yeah, there is an indirect relation between the two that comes because of the circuits that we design. Uh, or to give you more insight, so let's take a very basic circuit that we have in a MOSFET. It is, we use a resistor, then MOSFET, and let's say this is gate. This is VDD. Okay. So this is the basic CS amplifier. Okay. Now in this basic CS amplifier, I provide some VG, I get or VGS, and I get some output. We call it is across VDS. So when I apply, let's say 5 volts of VGS, I'll get some VDS of like, let's say my when I'll apply, let's say 5 volts of VGS, I'll get some amount of VDS. Then let's say I am applying 10 volts of VGS. So will my VDS change? So it actually, what changes in your MOSFET is the current because of the change in VGS, and it indirectly affects your VDS because your VDD is constant. So in this type of circuit, you have an indirect relation between VGS and VDS. But if, let's say, you are in a lab and you are simply trying to observe your MOSFET characteristics, then maybe you can simply, if you apply some VGS with battery and you can apply some VDS with battery, you will still get characteristics, right? But here these two are independent of each other. Now in case of amplifier, they are made dependent on each other so that we can basically tune our outputs based on inputs. So that's why they are made like to be dependent on one another. But if you look into a basic MOSFET, then these two are actually independent. Like you can simply apply some voltage to your MOSFET's gate and other to your MOSFET's drain, considering like this type of configuration, or you can make it as a common gate also. But since we are very we are very used to the common source, so this also works. It's just that in amplifier we want them to work as we want them to work as a coupled thing, so that we can get the relative changes that we want. But ideally, if you look at them, they can be used separately also. So that is what I meant when I said that these two are independent. Not in the amplifier setting or in complete circuit setting, but in general, these two terminals are independent of each other. Or two, or I can say the two, what was I saying? Two terminals, two terminals or these ports, two ports are independent of each other. So that is what I meant. Am I clear? Like, is your doubt clear?
Yes, ma'am.
Okay.
Ma'am, in this circuit, if we write equation for VDS, it is VDD minus ID into RD. And
Yes.
ID is depends on VGS
Yes.
exponentially. So if
Yes.
VD changes,
No.
VDS also changes,
First
right?
of all, not exponentially. It's quadratic.
Okay.
Yeah. But that's what I'm saying. In amplifier setting, VG and VD are dependent. But when you look at a MOSFET itself, then there is no dependence between VGS and VDS. In amplifier setting, we make it such that we can we can have some dependence, because see, when there is a dependence, there is always a advantage that you can try to use it to control. So you can control it with a knob. If two things are independent, then you'll require two knobs to control both independently, right? But if one is linked with another, so if you tweak one knob, it can change in that particular area, as well as it will reflect in the other part where these two are dependent. So for example, if let's say for like circuit 1 and 2. So let's say in circuit 2, if I want to change my characteristics like IV, what I'll need to do, I'll need to change my VGS and also my VDS, and these two needs to be changed independently, both of them. You can change them. But when you look at your circuit one, there only by changing your VGS actually you can change your characteristics, because VDS is actually dependent on VGS. But ideally, if you see, these two can be used separately as well. But in circuits, we make it such that we can have some control. And using that control, we actually use it to design our amplifiers or the circuits that we need. So that is the idea. Hope I'm
Yes,
clear.
ma'am. Yes.
Yeah. So with this, let's quickly move forward. So coming to the first question. So today's first question is, here it is already given that ID is minus K VGS, VSG minus VT. So first of all, what type of transistor is this?
PMOS.
PMOS. So what are the conditions for PMOS and NMOS? If we quickly talk about their operation regions of operation for PMOS and NMOS and their conditions. So first of all, when does an NMOS turns on? When VGS is greater than VTH. Okay? When VGS is greater than VTH, the NMOS turns on. What will be the condition for PMOS? It is VSG should be greater than mod of VTH. Why mod? Because for PMOS you will need negative voltages. Is this clear? In PMOS all the voltages will be in negative, and NMOS all the voltages will be in positive. The terminal voltages I am talking about. Okay? Now let's second condition. So when is your NMOS in linear region? When your VGS minus VTH is less than VDS, then the condition is linear. Similarly, for the PMOS case, it is VSG minus mod VTH should be less than mod VST or mod लगाने की
I
ज़रूरत
think
नहीं है.
smaller, ma'am.
Sorry.
Smaller than VDS. In NMOS, to be in linear, VDS should be smaller. Should be less than.
VDS VGS minus VTH is, yes, sorry. VGS minus VTH is greater than VDS, so it is linear, and similarly it is VGS minus VSG minus mod of VTH is less than your VSD. In case of PMOS, then it is linear. Now, third, when your VDS is greater than your VDS is greater than your VGS minus VTH, then your transistor is in saturation. And similarly, VSG minus mod of VTH greater than VSD, VSD greater than VSG minus mod VTH, then it is in saturation. So these are the conditions that we know for both NMOS and PMOS. Now, yeah. Okay, so these are the conditions that we know, and we have. Okay, so simply let's write the current equations also for cutoff first. Let's A for cutoff. ID is 0. For linear, ID is mu n Cx W by L, VGS minus VTH minus VDS by 2 ka by 2 into VDS. Okay, so this is the basic formula that is used for MOSFET current. Now let's say VDS is very small. VDS is very small. In that case, what we actually do, we simply neglect this term, which will be the VDS square term, and we'll simply write it as mu n Cox W by L VGS minus VTH into VDS. So this is for linear when VGS minus VTH is much larger than VDS. I'm writing it for NMOS. Okay. So for PMOS, mu n will be mu p, and VGS, VTH, and VDS will change accordingly. So this is for linear, and C for saturation. When is the condition for saturation? When VGS minus VTH is much smaller than VDS. So this is the condition, right? At this condition, your ID is mu n Cox W by 2L VGS minus VTH of whole square. Okay. Now talking about your characteristics. So when we have characteristics, let's say our transfer characteristics, which is between ID and VGS. So it goes somewhat like this, right? So let's say here we have our VTH. So when VGS crosses VTH, you will get current. This is quadratic in nature. Whereas, okay, what about this region? In this region, what is the current? Below threshold, we call it sub-threshold. Sorry?
Yes, this is I think approximately zero. This cutoff region.
Approximately 0.
Mm-hmm.
Okay. So any other takes on this? This region is known as sub-threshold region. Sub-threshold region. The region just before the threshold. So one answer that we got is it is approximately 0. So I want to know, first of all, is it 0? So what is your take? Is it like cutoff region that your current is 0? Or if it is not 0, then what type of current is it? Is it linear, quadratic, exponential,
Ma'am,
or
diode current
cubic?
will be there.
Diode current will be there. So what is the behavior of diode current?
Exponential.
Yes. So in sub-threshold region, your current is actually exponential. In subthreshold region, your current is exponential, whereas after threshold, your current behavior changes to quadratic. Okay? And it is never 0. Please keep that in mind. Below threshold, the current is never 0. It is very small, but it is exponential in nature. Okay? So this is what type of characteristics? This was transfer characteristics. Now what characteristics do we have? See, we said input characteristics is 0, since considering that Ig is 0. So we are left with output characteristics only. So ID, VDS. How does this characteristics look like? Your output characteristics. Sorry. It first rises, then it saturates. Ideally, it should be a straight line parallel to VDS. Practically, it looks somewhat like this. Okay. So first of all, what we call this region, this is the linear region that we are talking about when your VDS is small. Okay. And in this linear region, your ID is directly proportional to VDS. So it acts as a resistor. Okay. And since the slope changes with your VDS, or sorry, VGS, like for different VGS, you will get different curves in the slope changes. So different resistances you get. So we call it voltage controlled resistor, where the voltage that we are talking about is VGS, not VDS. Is this clear? So in linear region, your MOSFET acts as a resistor. Now, this region that you are seeing as a straight line, we call it as a saturation region, where your current basically saturates. So, if you, let's say, if your current is constant with changing voltage, what type of behavior is this? Or have you ever seen such kind of behavior? First of all, what will be the resistance in this region? When your current is constant but your voltage is increasing or changing?
Current source.
Current source, right? So why current source? Because here are, that is delta VDS, here delta ID. So R is infinite. And where else we find R as infinite? That is for current source. So in this region, we consider it as a current source. So yeah, in a MOSFET, we can use that MOSFET as a linear. In the linear region, it acts as a resistor, or in saturation region, we use it as a current source. In amplifiers, we use saturated transistors. So in amplifiers, we want current source model, or we use the current source model. So always when we are designing an amplifier, we try to keep our transistors in saturation region. Is this clear? In amplifiers, all your transistors should be in saturation region. Whatever transistors that you are using to design an amplifier. Okay.
Yes, yes.
So with this
Yes,
information,
ma'am.
let's
Mhm.
yeah. So we have talked about the basic MOSFET. So maybe we can move to our first problem.
So one question, please, before getting into this question,
Yeah,
this
sure.
problem. Can you please go to the curve? Yes,
Yes.
yes, the quadratic one, the ID versus VGS. So
Yes.
what I have deduced from your talk, that you mean that the origin point is only the cutoff region, right? And
Uh,
after
sorry.
exceeding this point,
I could
we
not
are
follow you.
using,
In this
yes,
curve, transfer characteristics, what were you saying?
yes. If we are at the origin point, the intersection point between ID and VGS, where VGS is zero, this means this
Uh-huh.
is the cutoff region, right? And
Yes, we can
exceeding
say
this
that.
point, we are in sub-threshold, since we are before the threshold. After exceeding threshold, we are
It
in
is
the own
quadratic.
region, linear or saturation, right?
So, yes. So it is, see, when we say linear or saturation, it is always beyond your threshold region. So, for checking whether your transistor is in linear or saturation, the first thing that you need to know is whether your transistor is on or off. So, when we say a transistor is on, so for cutoff, VGS is less than VTH, then your transistor is off. And ideally, we consider that current as zero in that region. But for linear as well as saturation, your VGS should be greater than VTH. In both the cases, your VGS should always be greater than VTH. That's when you consider your transistor to be on, and that's the next thing that you check is what is the condition of your VDS, whether VDS is greater than or less than VGS minus VTH. So,
Yes,
yeah,
yes.
that is the idea. Any other doubts?
And and why why should we have an amplifier in saturation? Why not in linear?
For an amplifier action, we use it in saturation region so that your So first of all, in saturation region, it behaves as a current source, and there is no dependency on VDS. And ideally, we want that current to be independent of VDS, and we can only get the dependence from VGS. Like so, we want to. So it's just like we only want to get the uh, output because of input voltage, output which is current, only because of input voltage. We don't want any influence because of VDS. So actually we want this characteristics, but due to other second order effects we get this type of characteristics, but ideally we don't want that. So this is non desirable. What is actually desired is this, where we only want to change our output current, which is the major output from the device, because of your input voltage only. You don't want any influence because of your VDS. So the idea for designing your amplifier also comes from that. So you want to use your transistors as your ideal current source. Yeah, that's okay. So
Ma'am, one more
yes,
doubt I am having.
yes,
Like in the, it is explained that below VT there is subthreshold region which is exponential current.
yes.
So how is it exponential? Like, is there any mathematical thing for that? Or
Yeah, there is a mathematical expression where you can actually, so it is derived from your diode characteristics, and it is an exponential current. It has a formula also. Uh, you can look for it in like advanced, advanced
Mhm.
notes, advanced notebooks or books,
Okay.
where you can look for the books from. Uh, like physics of transistor is a course. In that course we talk about advanced devices, so there we talk about these concepts. And I guess there is a book by Pirret, it is based on semiconductor devices. That book also has your subthreshold current, or even if you try to browse it on net, you can maybe find this exponential behavior of MOSFET current in subthreshold region, because actually it is quite useful, and nowadays people are looking into that also. So maybe you can also explore. But yeah, it is exponential, so there are mathematical formulas for that, so you can look into it.
Okay, thank you.
Yeah.
Excuse me, ma'am.
Yes.
Ma'am, you told that for a transistor to be in the off condition,
Hmm.
VGS should be less than VT.
Yes.
In the practical view, like for a diode, we have VT thermal voltage, which is 26 millivolt. We usually assume that.
Hmm.
Uh, in practical view, what if I keep a positive terminal at the gate and the negative at source, and
Hmm.
I'm measuring whether a transistor is on or off,
Hmm.
then what the value should I should arrive for the threshold voltage,
Hmm.
ma'am?
So ideally, it depends on how the transistor has been fabricated. Uh,
Is there any constant value that the threshold voltage should be around this value? I'm asking in that point of view.
no,
How
see, it
can I?
depends. Yeah, yeah, it depends on what MOSFET you are using. So generally, if you look into, say, your data sheets for that particular IC that you are trying to calculate, there you can, I guess, find the value of VTH, and how you will check whether you have attained your VTH or not. So you'll try applying voltages and check at what point your current suddenly rises. That is the point that you have attained your VTH, right? That sudden rise, which is quite high. So that shows your VTH. But ideally, let's say in this particular question, it is given zero point 0.9 volts, but for silicon normal MOSFET, it is 0.4, zero point 0.5 volts. It depends on the MOSFET specs, like what type of MOSFET you are using and what material MOSFET you are using. For germanium MOSFET, it will be different. For silicon MOSFET, it will be different. So it depends on what type of MOSFET you are using. And most probably, it should be there in your datasheet. Whatever MOSFET you are using, try to open the datasheet of that MOSFET, and the threshold voltage is mentioned in that MOSFET. For that MOSFET in that particular datasheet. Yeah. And that Vt which you are seeing over here, this is not thermal voltage. This is threshold voltage. These two are two different things. Ideally, we denote it as Vth. In this problem, it has been shown as Vt. But ideally, it is shown as Vth. That is V threshold. Yeah. Is this clear?
Yes, ma'am. Yes, thank you.
Okay. Any other questions? Anything from chat? Was there any question from chat?
Ma'am,
Yeah.
is pinch of voltage and VT are same, no?
Sorry.
Pinch of voltage and VT are same, no?
Pinch off voltage and
VT
so pinch off
output voltage.
voltage, VGS minus VTH is known as pinch off voltage.
Okay, okay.
This VGS minus VTH when it reaches your VDS. So when VDS is VGS minus VTH, we call it as the pinch off voltage. Okay. Any other questions? Okay. So let's move ahead and solve this first problem. So in this problem, it is mentioned that the ID's formula has already been given. Minus K VSG minus VTH. VTH of whole square with K being 28 millisiemens per volt. VT is 0.9 volts. Vx is 1.9 volts. Small Vx is 4 millivolt. What is the small signal ID? Give your answer in microamperes. Your answer in microamperes. The convention for current is to measure the current going into the node. Going into the node as positive. So yeah, here it has been clearly mentioned that the convention for the current is measured like the current going into a node. So here you have seen a negative sign. That is because the current that is going out of the node is considered as positive, and if current going into the node, here it is considered as negative. So that's why that negative sign. So yeah, first of all, let's find out what is the value of ID. What is the value of ID? We have all the values of VSG, VTH, K, everything. So what is the value of ID over here? You have to simply use this formula. Which is 28 Siemens per volt. VSG, what is VS 3.3 minus VG 1.9 minus VTH is 0.9 of 4 square. So ID that you are getting is how much? The value of ID that you will be getting is, can anyone let me know like what is the value of ID that you are getting? Now is this what we actually want? The ID that we are calculating out of the formula, is it the same ID that we actually want or which is asked in the question?
No.
No. So this is actually the formula for DC current, right? Now what has been asked is there is a small voltage change of 4 millivolts. So corresponding to that voltage, what is the current that you can see, which is the small ID. So how do we calculate the small ID? So it is like dID by dVx, which is our minus k Vs minus Vx minus Vth whole square d upon dVx. We'll get minus k into 2 Vs plus minus Vx minus Vth, right? So this small change in ID is our small ID which is asked in the problem, and the change in Vx is the small Vx that has been applied, which is equal to 2k Vs minus Vx minus Vth. So the small ID will be 2 into k Vs minus Vx minus Vth into small Vx. So small ID is 2 into 28 millisiemens per volt, 3.3 volts minus, yes, what will be the voltage that we'll be using here? What is the value of Vx? What is the value of Vs? Vx? Will it be 1.9 volts or will it be 4 millivolts? What is the value that we will be using here?
1.9.
1.9, because so this is part of your DC current, right? So 1.9 minus 0.9 into Vx, for that we'll use 4 millivolts. So we have to solve this and we'll get the ID. So what is the value of ID that you are getting? Small ID. And also let me know the units. What will be the unit? What is the value?
It's 112 micron amps.
112 micro?
Micro.
Are you sure?
Yeah.
Okay.
Yes, I
Yes,
Yeah.
recheck. Yes, yes.
it is microamps. So please be very sure with the units, because you might get the values correct, but if you get your units wrong, then it's completely wrong. So please pay attention to your units as well. Now, one more thing. What does change in ID by change in Vx mean? So what does change in I versus change in V? This term. What is this?
It's GM.
Yes, GM, conductance. So which is opposite of resistance. So dID by dVd, or let's say di by dV, is Gn, which is 1 by R. Okay. So if somebody asks you to calculate the conductance, it is actually this formula. This is the formula for conductance. Okay. Now moving on to the second problem. In this problem, the K is given, Vt is given. There is a resistance, extra resistance, which was not there in earlier problem. So in this problem, we do have Rd. So yeah, somebody was asking whether VGS and VDS are dependent or independent. In this particular circuit, if you observe very carefully, your VGS and VDS are separate. So if this was not shorted and if I apply two excess with same voltage 1.9 volt and 1.9 volt, so here your VGS and your VDS are both independent of each other, right? They are not dependent of any one. Like there are two voltage sources, one I have applied to your gate, whereas other has been applied to drain. So that is what it is meant when we say they are independent. But in the next problem, here if you observe carefully, here these two are actually dependent, because now this RD will actually change the drop across this transistor, which is your VDS. And this RD's drop depends on your current. And the current, because see, I already told you that your transistor is in saturation. And when the current is in saturation, so ID is a function of VGS only. It is not a function of VDS, considering an ideal MOSFET. Okay. And when there is nothing extra mentioned, we consider that the transistor has been considered to be ideal. So in that ideal case, your ID is always a function of VGS. But because of that ID, the drop across this RD will change, which will change your VDS. So it makes them dependent on one another. Whereas in the previous case, they would work separately. Like they are not linked with each other. Ideally it was shorted, so you can give one voltage, but if you remove them and make them as two terminals, you can apply separate voltages to both the terminals and they will work as independent terminals. Okay, so yeah, in this particular question RD has been introduced. Now we have to calculate the ID. So we have to calculate ID. So how will we calculate ID? We know the formula for ID, right? It is again the PMOS, so we'll use the same formula which was mentioned earlier. VTH whole square. Here it is minus K. VS is 3.3.
Ma'am,
Yes.
ma'am, the above, how did you arrive the above equation? ID equal to function of VGS, because
Yes.
saturation region is comes under the relation between VDS versus ID, no, which is output characteristics. How can you
Yeah.
write it as a function of VGS?
See, when I say a MOSFET is considered to be an ideal MOSFET, that means I want this characteristics, which is like ID completely parallel to VDS. Now, if I'm saying that ID is not changing with VDS, because this is the saturation region, right? So, is there any relation between ID and VDS, considering that ID has no change or VDS has no impact on ID? Can we say that ID is a function of VDS? No, right? But yeah, it changes with your VGS. Definitely, it changes with your VGS, right? So that's why it is a function of VGS. But with VDS, since it is always constant, so it is not a function of VDS. That's why in saturation, your MOSFET current is always a function of VGS, not a function of VDS. Clear? Yeah. So here we have Vs, that is 3.3. Vg, what is the value of Vg over here? Minus VTH is same 0.9 whole square. What is Vg?
VG can be the ID into RT.
Yes, Vg is
ID
actually
into RT.
Vd and it is Id into Rd. So we'll simply substitute it over here. So minus K 3.3 minus IDRT minus 0.9 whole square. So we have to solve this equation. Here, what is the unknown? The only unknown is ID. We have to simply solve this ID and we can get a value of ID, right? So what will be the equation? So this equation needs to be solved. So how many solutions we will get for ID? So considering that this is a quadratic equation,
Two
on
solutions.
ID we'll get two solutions. So I have already solved this equation. You can solve on your own, but I'll let you know the values that I've got. So one value is 0.6 milliamperes and other is 0.68 milliamperes. Now these two values are very close by, right? How to decide which one is the correct value of ID? Yes. How would you decide that what is the correct value of ID? What is the condition that your transistor needs to satisfy?
Yeah, we'll find the gate voltage, and
So
then we can do the
we
VSG.
need to have like VGS, or since it is a PMOS, I'll simply write VSG should be greater than your VTH, right?
Yes.
And secondly, your VSD should be greater than VSG minus VTH, right? These two conditions need to be satisfied. है ना? So let's look at the first condition, that is VSG should be greater than VTH. So VS is 3.3 minus how much is the VG? It is ID into RD. This should be greater than how much? 0.9. So let's say for ID of 0.6 milliamperes, it is 3.3 minus zero point 0.6 milliamps into how much is the RD? 3.76 kilo ohms. Kilo ohms. So, what is the value of this VSG that you are getting? How much is the value of VSG?
It's 1.044.
1.044. So, which is greater than 0.9
Yeah.
volts.
Point
Right.
zero.
This is okay. Now let's check it for our second. Yeah. Let's check it for our second value of current, that is 0.68, right? 0.68 milliamps of ID. Now what is the value that you're getting for 0.68?
It's 0.74.
0.74 volts. It is less than zero point 0.9. So we cannot have ID of 0.68 milliampere. So what is the value of ID? That is zero point 0.6. Right? So we have got it with the first condition. You can get it with the second condition as well. Now sometimes what might happen that the one condition might satisfy for both. Like for example, this conditions would have satisfied, but VSG would not have satisfied, right? So when can you be very sure? So if these two were satisfied and now you are calculating the condition for VSD, in VSD any one of the two conditions will fail. So that's when you know the correct value. Am I clear? Any doubts in this? Like how we have concluded that what is the actual value of current? Okay, since there are no questions, so
Ma'am,
considering
can
it
you
is
please repeat the procedures once again, please?
okay. So what we did, we have tried to calculate the ID. We have already known the ID value, right? ID expression, which was given in the last question. What was unknown was VG. Now from this particular circuit, we know that VG is equal to VD. And what is VD? This is source, gate, and drain. So what is VD? VD is ID into RD. So in place of VG, what we did, we have substituted ID into RD. And there a quadratic equation will be formed. We have to solve that quadratic equation. Now after solving the quadratic equation, since quadratic equation has two roots, so we have got two answers. Now we have to decide which one of these two is a correct answer. So for a MOSFET, I've already said that when you're working on amplifiers, you want your transistor to be in saturation mode, right? So when you want it in saturation mode, what are the conditions that need to be satisfied? So the conditions that need to be satisfied are first, your transistor should turn on, right? And second, the condition for saturation. So we will check these two conditions by substituting the values of current. So we started with the first expression where VSG should be greater than VTH. So this is Vs, this is Vg. Now we were trying to calculate if VSG is greater than VTH. So for zero point 0.6 volts, we have got it correct. But for 0.68 volt, it was incorrect. This is Vs, this is Vg, right? Vs, Vg. So which shows that zero point 0.6 zero point 0.6 milliamperes is the correct answer. Is this clear?
Yes,
Excuse
ma'am.
me, ma'am.
Yes.
Ma'am, can we solve this using KVL?
KVL. Where KVL?
Ma'am, can we apply KVL rule from top to bottom, from 3.3 volts to RD, and then form an equation? Then, ma'am, in that way, can we solve it?
Mm, so how will you apply your KVL? Because you're
Ma'am, it will.
okay. So it is like 3.3 minus VD is here it is VSD minus VSD minus
Minus
IDRD
IDRD.
equal to 0. Okay.
And then
So
VST will be correctly.
But
or
here 3.3, what will be your VSD?
ma'am, it will be root over ID by K plus VT.
Okay.
From
So,
the current
what
equation.
are you saying? So, you want to get your ID value from this equation. That's what you're saying.
Yes, ma'am.
You can get your ID value from here as well. That is also fine.
Okay.
Yeah. But how will you? Okay, considering that VD is equal to VG, and from there you will
Yes.
substitute this equation into there.
Yes,
Yeah,
ma'am.
you can go ahead and solve that way also. That's fine. Now moving on to the next problem. Okay, so in this particular circuit, it is a N-type MOSFET, right? So in this N-type MOSFET, ID has been given, K and VT are given, R1 and R2 are given. What is the maximum value of RD for which the device is in saturation? So you have to find the maximum value of RD to keep device in saturation. So what is the first step that you'll do to solve this problem?
I think we need to get the V overdrive first.
V overdrive first. So V overdrive we can get by, since we have these values of resistances, we'll use the voltage divider and we'll get the value of this VG, right? So what is the value of VG that we are getting? It is 5 into. So the value of VG that you will get is actually 0.74 volts. Now VT is already known 0.5. So this VG is actually VGS, since there is nothing between your source and ground, so it is VGS. Now here you have your VGS, you have your VT. What will be the next step with all
Find
the
the current,
givens? You can
saturation
simply
current.
find the saturation current, VGS minus VTH whole square, that is 1.6 millisiemens per volt into VGS, that is 0.74 minus 0.5 whole square. So the current that we'll get after solving this equation is 0.067 milliamperes. This is the current that we'll get. Okay. So we have got the current, right? So this is the current that is flowing through your transistor. Now, what was the question? We need to find the RD max, the maximum value of resistance which can keep your device in saturation. So, what is the governing equation to find to keep the device in saturation?
That VDS should be equal or greater than V overdrive.
VDS should be greater than or equal to the operational voltage, that is VGS minus or overdrive voltage, that is VGS minus VTH. So here this is VD. So how will you write VDS? It is VDD minus IDRD, right? IDD minus IDRD is VDS should be greater than equal to your overdrive, which was 0.24, right? So from here we will, okay, let me write it in expressions. Minus VDD, so which is 5 volts, right? So 5 minus RD, IDRD to be minus 4.76 volts. So IDRD should be less than equal to 4.76. RD should be less than equal to 4.76 by ID. What is the value? 0.067 milliamps. So which gives your RD should be less than equal to, when you solve this equation, the RD value that you'll get is 71.04 kilo ohms. Any doubts in this solution? Any doubts? Anyone? Hope there are no doubts. So let's move ahead to the next problem. So this was question number 3. So question number 4. In this problem, so same as earlier question, we have to use the same circuit. Yeah. So in the same circuit, is it is given that your RD has been changed to like 35.5 kilo ohms. What is the maximum current that can flow through the device such that the device is in saturation? For this question, ignore the earlier values of R1 and R2. Okay, so uh, okay, so here the idea is for
Excuse
the
me, ma'am.
given, yes,
Ma'am, as we've watched the lectures, sir, the instructor told that this circuit is not a good practice for an ideal MOSFET. Then how can we further find some independent value from this, ma'am? This is not our circuit
which circuit,
to work
which
with.
circuit,
Um, the circuit which doesn't consist of source resistor.
which
For an
doesn't
ideal,
consist of source resistor, right?
yes, here
So
we,
did sir talk about source degeneracy? Did he teach about anything with source resistance, its importance and everything?
yes, ma'am, yes, ma'am.
So it will come in near future. So you will clearly see the differences, and even sir will talk about it. Like, why do we need source resistance? What is the importance that it brings in? So it actually introduces a more stabilized circuit and everything. So it will come in theory as well as when you do problems, you'll get the problems based on like very simple circuits, and slowly we'll move towards the complex circuits as well. So we are starting with the very basic circuits and slowly we'll move towards the complex ones. So that is the idea. Okay. Is this fine?
Yes, ma'am.
Okay. So yeah, in this problem, it has been given that RD is 35.5 kilo ohms. So RD has been fixed. Now we have to find what can be the maximum current that we can draw out of the circuit, considering that the R1 and R2 values which were there earlier are not present. Okay. So the only thing that we know is 35.5 kilo ohms. With this 35.5 kilo ohms, what can we find? So VDD is IDRD plus VDS. This is what we know, right? Now, here, this VD to keep it in saturation. What is the condition that it needs to satisfy? Your VDS should be greater than or equal to VGS minus VTH, right? So the minimum voltage at least that you need across VDS is VGS minus VTH. So let's say VDS is VGS minus VTH, right? Now for this, if let's say your VDS is VGS minus VTH, so we know ID is K VGS minus VTH of whole square, assume. So if that is the case, then ID equal to K VDS whole square. So from here you can derive the value of VDS as root under ID by K, right? So we'll substitute this into this first equation. So VDD is equal to ID RD plus root under ID by K. So what we can do is we can simply make it like VDD minus IDRD equal to root under ID by K, and we can square both the equations. With this we'll get a quadratic equation where the variable will be again the same ID. So the equation will be like VDD square plus ID square RD square minus 2 ID RD VDD equal to ID by K. So we have to solve this equation with respect to ID. When we solve this equation with respect to ID, again considering the equation being a quadratic equation, we'll get two values, and the solutions that we get are 131.365 milliamperes and the other solution is 151 milliamperes. Now again see here we are getting two values, right? So which one to consider? Which one is the correct value of current? Which value is correct? How to find out? How to find out which value is
I think
correct?
the value that will give us VDS equal V over drive.
VDS equal V over I. But the point is, how would you know VGS? Is there any way you can get your VGS? Because you don't know R1 and R2. Nothing is given. Only you know RD. KVL? But what will you get out of KVL? How would you use KVL? Can you elaborate? Okay. So yes, the answer is right. We will use KVL. The only KVL that we can use is VDD equal to IDRD plus VDS. So here, what can we do? For sure, one thing that we know is VDS should be positive. This is clear to everyone. This VDS will always be positive, right? Am I right? Or will we, is there any chance that we can get this VDS negative also? For the condition that the transistor needs to be in saturation. For saturation, your VDS will always be positive because VGS minus VTH will always be a positive term, right? So since VGS minus VTH is a positive term, VDS will definitely be a positive term. So now what we can do, Let's check for VDS. That is VDD minus IDRD. Now here what we'll do, first we'll check for 131.365 milliamperes. So here the VDS that you will get is 5 minus 131.365 into 35.5. Yeah, so what is the value of VDS that you are getting? Is it positive or negative? Now second for 151. So what is the condition? Are you getting both positive, both negative, one positive, one negative? So okay, when you will solve, you'll get a positive value for this, whereas negative value for 151. So which makes your final answer is 131.365 milliamperes. I'm rushing a little fast because it is already 7:40 and we still have problems to solve. So just in case if you have any doubt, you can ask me now or we can discuss after the session as well. I'm okay with that. Hope this is clear. So now moving on to the next problem. So in this problem again the same.
Ma'am, please, I have a
Yes.
question.
Yes.
Are you
Go.
sure that the ID is 131 milli?
So you have
Because
to
this,
solve this quadratic equation. The moment you solve this quadratic equation, substituting all the values, you can get these two values. Now, the only thing that you know is RD. So the
yes.
only equation that you can use is a KVL from VDD to ground,
Mhm.
which
I'm
is
just
this
saying, I'm just
VDD.
asking because ma'am, sorry.
Huh,
I'm just asking because 131 is milli and 35 is kilo.
sorry,
So this
170.
131
Huh, is
131
milli.
is milli and
Yes.
35 is kilo. This
70.
resultant I think is higher than 5.
So that's what I'm asking. Is it higher than 5?
This and the second one, both of them will be higher, I think. Or I am wrong. I don't know.
Okay, wait.
131
Current
milli
should be
and
in
kilo.
micro. No. It's not
Yes,
milli.
micro.
It's micro. Yeah, it's micro. Micro. That's when your values will come micro, right? Yeah, it is in micro. So the currents are in micro, and with that, when you multiply your kilo ohms, so it will be in some points, right? So from there, you can find like what is the value that you are getting, whether it is positive or negative. So it is micro. Actually, here it is also mentioned like give your answer in micro, no? So the value is actually in micro. Yes. Okay. Hope the method is clear, like how we are trying to get to one like particular solution when we are getting to solutions. So is this clear? Out of two roots, see it is very important to figure out when you're getting multiple roots, like which one is actually the correct answer. And we have used till now we have used two methods. So this one is a bit tricky one because here we only know like the value of one resistor. And earlier it was a little easier because there we could directly use the concept of the transistor saturation equations and everything. So yeah, that is the idea. Okay, so moving on again, based on the same question, like same circuit, we have. So here we have to repeat the values of R1 and R2. So that is R1 and R2 is 575.7 and 100. 575.7 and 100K. Okay. and this was 35.5K. Yes, 35.5K. So in this circuit, it is mentioned that due to the temperature and other device imperfections, the value of K is 2 times of K. So the K that was earlier 1.6 millisiemen per volt has become K dash, that is twice of K. So the question is, will the device still be in saturation? So for this particular condition, it's 1.16. 1.16. 1.16 millisiemen per volt was the earlier condition. Now it has become K dash. So the question is, will the device be in saturation? So what will be the first step that we will do to solve this problem?
I think we need to find the ID, and from ID we'll get VDS and the chip.
Yes. So first we need to find the ID. We already know the VG. How much was the VG? How much was the VG that we got last time? 0.74. Yeah. So it was 0.74 volts. So we already know the VG. So VGS minus VTH is already known. 0.24 volts. So now the ID dash, which has been changed, it is 2 times of 1.16 into 0.24 whole square. So the ID dash that we will get is 0.1336 milliamperes. Now with this ID, what we will do, we will try to find the VDS. So VDS is how much? It is VDD minus IDRD. So that is 5 minus 0.1336 into 35.5. So what is the VDS that we are getting? The VDS that we are getting is 0.278. Okay, 0.278 volts, and this VDS is actually greater than your VGS minus VTH. That is 0.24 volts. So yes, transistor is in saturation. Is this clear? We simply found the ID and we applied the KVL, and using that KVL, the value of VDS that was found, it satisfies the saturation condition. So the transistor is in saturation. Hope this is clear. Okay. So see, if you won't ask me anything, I won't get any response, I'll consider that everything is okay, like you understand, and I'll move ahead. So just in case if you have any questions, kindly stop me and ask. Okay? Sure. So in this problem, it is again an N-type MOSFET with the VT of 0.5. R1 is 654, R2 327, RD 22.7, and this is again 22.7 kilo ohms. All are in kilo ohms. So yeah, somebody was asking the use of RS, right? So we have arrived at the problems with RS. So in this problem, K is 4.7 millisiemens per volt. Yes. So in
And
this,
previous
what is, yes?
previous question.
Previous question, okay? Yeah.
Is it in saturation now?
Sorry?
Once it's last, you wrote it is in saturation.
Sorry?
Uh, you have written that transistor is in saturation only once it's the midpoint. How is it in saturation?
Transistor is in saturation, right? Because VDS is greater than VGS minus VTH. What is your doubt
What
here?
what is VGS value? Ma'am? VGS minus VT value.
VGS minus VTH is here, right? 0.24,
Okay, thank you.
which was from the previous questions.
Okay, ma'am. Okay.
Because it is the same circuit, just the analysis
Okay.
has been changed. Yeah, it is very
Okay.
good. So yeah, moving on to this problem. So here again we have to solve the value of ID. So now how will we solve the ID? First of all, again, since the transistor is in saturation, first step, find VGS. Okay, find VGS. But from voltage divider rule, what you'll get? You'll only get VG, not VGS. Because S is not ground over here. This is VGS. Earlier, this was VGS. The difference is clear. Is the difference clear from the last question to this particular question? So it increases the
Yes, ma'am.
complexity. It increases basically when there is a source resistance, it actually increases the complexity of your circuit. But with increased complexity, it actually stabilizes your circuit. Okay? So yeah. Here first thing is we'll find the value of Vg. So how will we find the value of Vg? It is 5 into 327 by 654 plus 327. So the value of Vg is, I have already solved it, it is 1.67 volts. Now, uh, how will you find Vs? So Vs is Id into Rd. So when we say VGS, it will be 1.67 minus, oh sorry, this is Rs, Id, Rs, right? Now when we say VDS, what do we mean by VDS? We mean VDD minus IDRD. Is it okay if I write VDS as VDD minus IDRD?
No, no. This is VD.
Sorry?
This is VD, not VDS.
Yes, this is VD. So when I say VDS, so it needs to be this, right? The particular voltage drop across the transistor only. So for VDS, I need to have extra ID into RS. So that everything beyond this drop across RD and RS will give us VDS. So 22.7. Yeah. So here, sorry. We know VGS, we know IDS. ID, what is ID? It is K VGS minus VTH whole square. So ID is K. VGS is 1.67 minus IDRD or RS minus VTH whole square. So we have to solve this quadratic equation again to find the value of ID. Still, we'll get two values. One is 47 microamperes and other being 56 microamperes. With these two values, now we have to see that which one actually satisfies our condition. So yes, it is 47 microamperes. So how did you finalize 47 amperes? If you can let others as well know. Like what was the method of segregation for you, whether it will be 47 or 56. Hello? How did you conclude it, Sanjeet? Yes. Sanjeet, how did you conclude whether it will be 47 or 56 microamperes? If you can share with others. The answer is correct. It will be 47. But how?
I think we will see which one will get positive VDS.
Yeah, which one will get us the positive VDS, and you can also check like VGS should be greater than VTH, right? VTH, VGS is a function of ID and RS. So from here also you can get it. From here also you can get it. Anyways, you can confirm it. VT was already given. So yeah. So the final answer is 47 microamperes. So let's say if I go ahead with this VGS minus VTH1. So the first for ID of 47 microamperes, VGS is 1.67 minus 47 micro into 22.7 kilo. This and for second ID is 1.67 minus 56 micro into 22.7 kilo. So how much are we getting? So here 1.67 minus 0.47 into 22.7. Yeah. We can use any condition like this VDS. So this is one condition. This KVL is another condition. And the third condition can be, so maybe I'll write and write. So 1, 2, and third condition that we can check is VDS should be greater than VGS minus VTH. So we can check using any of these three conditions. And in any of them, if we find like the correct value, then that will do.
Can I ask a question, ma'am?
Yes.
Why in such questions we do not say that if we have a quadratic equation and we end up having a quadratic equation with two solution,
Yes.
not choose directly the smaller current.
Mm, yeah, actually, we can say that way too, because
Without checking.
without checking, no. But we just
I think maybe we can get in the cases where the two currents are satisfying VGS and VDS, but not satisfying the saturation condition. I think so.
yeah, saturation condition might get hampered because that might be a case where you can get like VDS is less than VGS minus VTH. If that type of condition appears, then there would be a problem, I guess. So it is 0.6. Yeah, that's why it is better to check and be very sure with the one, just to not sleep, not slip into linear condition or this. So yeah. First of all, the basic condition that we should always check is whether the transistor is being on or not. That is the very first condition that we should check, like VG is greater than VTH. Because sometimes what happens, your VDS condition is satisfied in few questions, like I have come across those type of questions where your VDS condition actually satisfies, but it is this VGS greater than VTH, the first condition, that actually doesn't satisfy. And it actually confuses people that okay, like VDS condition is being satisfied, but still why the question is wrong? Because the catch was the critical path was not, so the critical part was not the VGS thing, it was actually the VDS, VDS greater than VGS minus VTH was not the critical equation over there, but it was rather VGS greater than VTH. So yeah, so we should always start by checking this first problem, that is VGS greater than VTH1. Then we should move ahead with the VDS problem, that is VDS should be greater than VGS minus VTH, which is the saturation condition. So first you should always check the turn on condition, that is 1. Then you can either go for, so these two are similar, right? These two are same thing. So this is for saturation, this is KVL. So you can go for any of them, but this should be second and this should be third. So that's how you can get it. Yes, VGS greater than VTH is to check whether the device is even turned on or off. So this is for on-off condition. This is for saturation, and this is basic KVL. So you should go in this pattern, like 1, 2, then 3, to make sure that your device is on and it is working in saturation and it is also satisfying your KVL, because KVL comes at the end, right? These two are at device stage itself, whereas this takes the interplay of your components as well, resistors and all, directly. So yeah, that is the idea. Okay, this was question 6.
Excuse me.
Yes.
Is there any possibility that both the current satisfy these equations?
There might be a possibility that, let's say, the transistor is turned on, VGS is greater than VTH, is satisfied for both the currents. Now, okay, so if it is satisfied, then you cannot select both of them as your currents, right? Answer should be only one current at a time for a given circuit, for a given condition. It should always be one current. But so what is the next step that you can do? So it is not the VGS greater than VTH1. So next you will check for saturation condition. That is VDS should be greater than VGS minus VTH. Most probably when you consider the second condition, you should get the answer. Or if you are unable to get the answer at that point also, then you can check for the KVL. But since the KVL is already considered in these two questions, like the impact of resistors are already there in these two, so you should get your answer by the end of either VGS greater than VTH equation or VDS greater than VGS minus VTH equation. So by the end of that, you can get your answer, like which one to select. Yeah, somebody was asking, like, how did we arrive at this VGS is equal to 1.67 IDRS? So in this particular equation, in this particular circuit, your S is not grounded. So there is a resistor between your S and ground. So the value you get from your voltage divider is actually VG, and the drop across your source terminal is from source to ground, whatever is the drop, that is your drop across source terminal, right? And we already know VGS means VG minus VS. So we have simply put up the values of VS and VG, and that's how we came with this equation. Hope this is clear. Okay, so it's already 8. Maybe we can do this another question which is linked with the previous question. Question number 7. In this problem, you have to find the GM. So GM, we did consider GM, right? in the previous. It was, what was the value? 2k VGS minus VTH, right? Or if I write it as 2k VGS minus VTH square by VGS minus VTH. So I can also write it as 2ID by VGS minus VTH GM, right? So using these formulas, we can simply get the values for GM. Is this clear? Any doubts? Okay. So moving on to the next problem, question number 8. So in this problem, it is asked to calculate the small signal gain. So when you are asked to calculate the small signal gain, ideally for this configuration, what type of configuration is this? It is a CS configuration, right? It is given that the capacitors are so large that they behave as short circuit. So when they behave as short circuit, so what are the two ports that you have? It is GS is your input port and DS is your output port. So the configuration is CS configuration, and in this CS configuration, for CS configuration, the gain, small signal gain, is GM RD. Simply GM into RD and negative. Why negative? Because you see a phase shift in your signals. Like there is a 180-degree phase shift in your signals. So the gain is GM into RD. Here the value of GM will be 2 into 47 microns by how much was the VOV? How much is the VOV that we are getting? Okay, we didn't calculate the VOV, right? Is somebody saying something?
So what was the value of the threshold? 0.5.
Yeah, it is
We
0.5.
calculated VGS. No, not 0.5. We calculated VGS in the prior question, and
Yeah,
V threshold is 0.603 is the VGS,
yes,
and
yes.
V threshold is
0.603.
0.5.
So 0.603 minus 0.5. So the GM that we'll get, and the unit is, yes, it is in microsiemens only. 2 into 47 microsiemens, and it is 0.103. Yeah, so what is the value of GM that you're getting? If any, would let me know. It will be in microsiemens, but what is the value? Maybe we can convert it to millisiemens. The value is large.
0.91 millisiemens.
4.91.
0.0.
0.91.
Mm-hmm.
0.91 millisiemens. Okay, maybe you can cross check. I have not calculated this answer, but considering this is correct, so let's say 4.91 millisiemens is the GM that you are getting. So for this particular question, the gain will be minus 0.91 millisiemens into what was the RD? It was 22.7K. 22.7K. So this will give us the gain of, what is the value of gain that we are getting? Gain of around 20, 21.
20.7.
20.7, right? So it
Mm-hmm.
is volt by volt. So what about the value of gain in dBs? What will be the value of gain in dBs? How will we calculate the gain in dBs?
20 log the answer.
Yes, it is 20 log. Log base 10 or log base E? Is it ln or
20
is
log
it
base
log?
10. Log, log.
Yes, it is log base 10. So please keep these in mind because sometimes uh, we like misinterpret and it goes wrong. So it is very important to keep this in mind. So yeah, so what is the gain that we are getting in dBs? Decibels?
26.
26 dBs. Yes, okay. So the gain that we have got for this particular circuit is 26 dBs. Okay. So now there are a few more questions, but they are in similar terms. It's just the PMOS has been changed to NMOS, and we have to again calculate the value of this R resistor so that it stays in the saturation. It is like the similar question that we did for PMOS, right? The same pattern it is for NMOS. So hope you can do this question, right? I'll post this so you can try this question out. Okay, since it is already time, so you can try this question out. It is just the change is N and PMOS. And when you see this lambda equal to 0 volt inverse, that simply means that you are considering an ideal transistor. That is, your transistor is behaving as an ideal current source. That is the idea. Okay. Now, considering question number 10. So, in this question, again, so here, again, it is a PMOS and you have to find the value of R2 so that your current is 90 microamperes. Easy, right? This is source, gate, drain. From current, you will get VG. From VG, you can find this resistance, right? So yeah, these are the 10 questions. And question number 11. So I guess there is another question 12. So question number 12 is similar to the questions that we did earlier. So it is the current that flows through the transistor that needs to be find out. The same question. And in this particular question, there are two transistors, M1 and M2, with different gate voltages and different threshold voltage, same threshold voltage, but their constant values are different. So with different, but the main idea behind this question is the current flowing through both the transistors is same. So here ID1 is equal to ID2. So in this question, you have to find the currents because gate voltage is given. You have to calculate the source, like use the source voltages VGS, and yeah, keep in mind that both are N MOSFETs, N type MOSFETs. With that, we'll find VGS2, VGS1, and by using that, we have to find the voltage of this. And the concept is ID1 equal to ID2. So this is the concept that needs to be used here. So yeah, this is the concept that you will use here. Saturation current formula that I have already mentioned, you will use that and you will get the value of this V out. Hope you can solve this. Just in case if you have any concerns, you can let me know as the form of a comment under the video, or maybe we can solve in the next class just in case if you have faced any difficulty. Okay. Yeah, so these were the problems that were there for this week. If we don't have any doubts, maybe we can break our session over here and meet in the next coming week.
Excuse me, ma'am.
Yes.
Ma'am, looking into the architecture of MOSFET,
Yes.
why we need to reverse bias the PN junctions, ma'am?
Why we need to reverse bias the PN junctions?
Unlike diodes, we should always reverse bias the PN junctions. Why do we need to do that?
So that is because we want the direction of flow in one direction, right? The flow of charges in one direction. So let's say if you provide a negative voltage to source as well as negative voltage to drain, so what will happen? It will start repelling your electrons. So where will you collect your electrons? But what we want is a path. So let's say we want the carrier path starting from source side to the drain side. So that means your drain should collect the charges and your source should actually push the charges away, right? But so how your drain will push the source will push the charges? So it will push your charges when it is relatively in the forward bias side, right? So that junction is forward biased, and drain side will start collecting your charges when basically it is reverse biased. Or if you think from a voltage perspective, if your source is relatively negative and your drain is relatively positive, so what will it do? Your source will actually push your electrons towards the drain side, and since the drain is positively charged, or positive drain has positive voltage, so it will collect your electrons. But if your drain was also negatively charged, which makes both your junctions to be forward biased. So in that case, what will happen? Rather than collecting your electrons at the drain terminal, it will start pushing your charges. So you will not see that flow of current that you want from your device. So that's why it is very necessary for one junction to be forward biased and other junction to be reverse biased, so that your charges can flow in that path that you create. Is this clear? Okay. Any other questions?
Yes,
So
excuse me, ma'am.
Yes.
Can you go about? Can you go a little bit upward?
Okay. Okay.
Yes. Again, again, again,
Okay.
until I tell you stop. Yes.
This question?
Again, 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 again.
Okay. Top.
Mm-mm. Yes, yes, yes. Question three.
Question 3. Okay. Yeah. Yes.
Yes, not this one. The prayer one. I think the one prior to this.
Prior to this,
Mm.
question number 2. This one?
Two. Yes, yes.
Okay.
I'm just a little bit confused. I don't
Okay.
know how this circuit is working because I can understand the equation. Theoretically,
Right, right.
I understand it, but practically, I'm not able to understand it because the
Okay.
current that
So
is moving
if,
in this device is dependent on the gate. So
okay.
how gate will gain voltage? Okay.
So first things first, the moment you look at the circuit, the thing that is very clear is the circuit will always keep your transistor in saturation no matter what, right?
Yes. Mm-hmm.
Because your VDS is equal to VGS. So VGS
Yes.
minus VTH is always smaller than your VDS. So your
Mm-hmm.
transistor always remains in saturation. So you don't have to worry that your transistor is in saturation or not.
No, no,
That
I'm
is,
not worried about the transistor in
yes.
saturation or not. I am for
So
sure of that.
yeah,
But
that
I am
is
I
one
am worried about
advantage.
the voltage of gate.
Voltage of gate is changing. That's what you're trying to say.
No, no, no. How we have voltage on gate since we don't
So
have current?
no, why we don't have current? We do have current.
Because current
Because
is dependent on voltage. Current comes after
yes,
voltage.
but see, the moment you turn on your VDD, there will
Mm-hmm.
be certain drop across this transistor, certain drop across this resistor, which will set up your circuit in a certain way that you will see a constant current flowing through this, which is basically you can say a stable condition when you'll see one current flowing through this circuit because of the value of this resistance RD. And that current, and if you equationally if you see, so you know how we have got the value of current. But practically speaking, the moment you turn on your voltage VDD to ground, there is a path to flow, right? There is a current
Mm-hmm.
path, so that
Mm-hmm.
path will set up and you will see a constant current flowing in that particular path. Yeah,
Mm-hmm. Okay.
there won't be any concern with that. But yeah, numerically, how to solve it, that is what we are trying to see. But we don't have to worry in terms of like whether this circuit will work or not. This will definitely work. And one more
Mm-hmm.
advantage that you get out of this configuration is you don't have to worry whether your transistor is in saturation or not, because your transistor is always in saturation in this particular configuration. So that is the
Mm-hmm.
advantage that you get. Yeah.
Yes, yes.
And
Thank you so
also
much.
you don't and also one more advantage that you can see is you don't need external voltage source for this particular circuit. Like
Yes,
your
yes, yes.
gate doesn't require any external voltage source or any extra resistors to be placed, so it reduces the complexity of your circuit and reduces the size of your circuit. So that is also another advantage that you can get out of this configuration.
It is self-biased circuit.
This is self-biased circuit, yes.
Mm-hmm. Thank
Yeah.
you so much for this great session.
Thank you for attending.
Ma'am, one doubt I'm having.
Yeah.
So, in the question in which we have calculated gain in dB using 20 log formula,
Yes.
so the actual gain was negative, like phase shifted,
Yes.
but we just considered absolute, like
Absolute
positive
values.
value. So,
See,
is there any reason कि just because log negative will not be possible,
no,
we
no,
are
no, no. That's not. See, the value gain is never negative. When we say negative gain, that basically the negative only shows you the phase shift. That doesn't mean the gain. Gain, how can a gain be negative?
Mm-hmm.
It
Okay.
can be
Yeah.
larger or smaller, but something, how can it be a negative value? Negative does
Mm-hmm.
not make any sense, right? The
Okay.
negative just shows you the phase shift. That's why when we
Mm-hmm.
are considering it in dBs, we use the absolute value, nothing beyond that. The
Okay.
negative only comes because of phase shift, nothing else.
Okay.
Yeah.
Thank you.
Thank you. Any further questions? Okay, so if not, maybe we can break here and meet next week. Okay. Thank you, everyone. Have a wonderful evening ahead. Good night. Bye.
Thank you. Bye.
Thank you, ma'am, very much.
Bye.
Thank you, ma'am.
Thank you.
Thank you. Bye.